Most systems in real life are not pure substances. Most systems are composed of mixtures of various atoms and molecules that conceivably can have very different properties from one another. That's something we've ignored in this class up until now, but we need to incorporate it into the modes of analysis that we're already very familiar with. So imagine that we're given an ideal gas, and we're told that it has the following molar fractions, that it is 50% oxygen, 30% methane, and 20% nitrogen. Well, these are molar fractions, so what that tells you is if you have a kilomole of the substance, the entire mixture that is, then you have half a kilomole of oxygen, zero point 0.3 kilomoles of methane, and 0.2 kilomoles of nitrogen. That's what those percentages refer to. Okay, so imagine that we want to figure out what the mass fractions of this substance are, namely, by mass, how much of the substance is oxygen, how much is methane, how much is nitrogen. The very first thing I would do in analyzing any problem of this sort is to construct a table, because you'll only get so far with subscripts. So on the leftmost side, the first column, I just have the three molecules. Then I have various variables, both in terms of molar fractions and mass fractions, that we want to fill in. Ultimately, our goal here is to fill in this entire table. So let's start with the first variable, little n. Well, little n is the number of kilomoles of a substance. Now, we actually don't know how much mixture we have, so it's a little tough to give little n in some absolute sense, but what we can do is we can quote little n in terms of kilomoles of a particular molecule per kilomoles of mixture. So for example, if we assume that we're dealing with 1 kilomole of total mixture, then we can figure out how many kilomoles of oxygen there are, how many kilomoles of nitrogen, and so on. Well, actually, we already know that. I already went through it, right? We said that if it's 50% oxygen, if you have 1 kilomole, you must have 0.5 kilomoles of oxygen. So, in units of kilomole per kilomole of mixture, we know those values. It's 0.5, 0.3, and 0.2. That's all you have to do with little n. And just to make sure, at the end, that you did all your counting right, those three numbers should sum to 1, right? Because ultimately, there has to be 1 kilomole per kilomole of mixture for the entire mixture. Okay, so we have little n. Now we need the molecular weights in the next column. Well, those are easy. You just look those up in the back of your book. Molecular weights for each of the three molecules, I just put in there. Okay, and those are in kilograms per kilomole. Next column is little m. That's the number of kilograms of a substance. Now, again, we don't know how much mixture there is, so it makes sense to quote kilograms per kilomole of mixture. And we just want to know like how much oxygen there is in kilograms per kilomole of mixture. So for the first row, how do we get that? Well, you can see actually if you multiply little n times big M, you'll actually get units of kilograms per kilomole of mixture. So all you have to do is multiply those together. That will give you out a little m value, in this case 16, with units of kilograms per kilomole of mixture. So under the assumption we're dealing with 1 kilomole, that tells us that we have 16 kilograms of oxygen in that kilomole of mixture. And we can go through and do this for the other two rows. So we go down to methane, exactly the same process generates 4.812. Same process for nitrogen gives us 5.602. That's in kilograms per kilomole of mixture. Now an interesting detail, when you add in the values of little m for all three of those rows, you get a number 26.414 kilograms per kilomole of mixture, but that accounts for the entire mixture. So what that tells us is that the effective molecular weight of the entire mixture is 26.414 kilograms per kilomole. Good to know. Alright, last column. This is the mass fraction, and it's usually quoted as a percent. You could write it as a decimal too, it doesn't really matter. Ultimately, what we want to know is relatively how much mass does oxygen make up for this mixture compared to methane, compared to nitrogen. So to calculate the mass fraction as a percent, over here we'll treat oxygen first. What I'm going to do is take the ratio of this value, little m for oxygen, divided by the total sum of all the little m's for all three components in our mixture. So we do that and then multiply by 100%. So it's just 16 divided by 26.414. You'll see the units cancel. We're getting out a unitless fraction. Multiplying it by 100% will give us a percent out. So we do that, and we find that the mass fraction for oxygen is 60.57%. So now let's enter that into our table. We'll do a very similar procedure for methane and nitrogen. So in the case of methane, it's 4.812 divided by 26.414 times 100%. That gives us a mass fraction for methane of 18.22%. We'll put that in the table. For nitrogen, we end up getting that it's 21.21%. We'll put that in the table too. Few things to note. One is, these mass fractions are telling us by mass how much of the mixture is made up by a particular substance. So this means that by mass, oxygen, for example, makes up over 60% of the mixture, even though it was only 50% of the mixture by mole. That makes sense. The different molecules have different molecular weights, so their mass weighting is different than their molar weighting. Next thing to note, at the end of this, of course, you can do a sanity check because it should be the case that the mass fractions sum to 100%. So we look over those three numbers in the rightmost column, 60.57 plus 18.22 plus 21.21, and sure enough, they add up to 100%. You can imagine in a real problem, you might be off on the last significant digit depending on how you rounded. It ought to come pretty darn close to 100% or else you messed up. That's how we do a mass analysis given a molar analysis. You can probably see a very clear path if you were given the mass analysis to go back through and get the per mole quantities just as easily.